Hello everyone. So in our previous session we were talking about the history of organic chemistry, and we saw how chemistry was focused on the development of organic compounds, and even though not only in the synthesis but also in some catalysis process for the breakdown of complex organic structures, like those examples of catalysis developed by Kirchhoff that were proved to be useful not only for the decomposition of um, complex organic compounds, but also for the synthesis of some fats that were even not only able to reproduce organic fats, but also to the production of different types. So all this happened during the 18th and 19th century. But in parallel, in the field of physics, there were also some developments that finally allowed to link both sciences in what we know physical chemistry. In a previous session during the scientific revolution, we say that some early attempts of physical chemistry were developed by people like Boyle, who developed some of the basic theories uh, about the relationship between pressure and volume and temperature. But now we will see that the people in the 19th century gave a step farther and developed some of the theories that we still use today in our lab practice. So let's start. Thank you. During this session, we will talk mainly about the developments of chemistry in the field of physical chemistry during the 19th century. But for doing so, we should start with the development of the periodic table of the elements. And first, we should say that the first attempt to do an order or to organize the elements by atomic weights, it was done by John Dalton, as you should remember from a previous session. And from his first attempt, we know that there were some mistakes, and we discussed it in the previous session, but we also saw that it was corrected by the development of the theory of valence and the more precise measurements by Gay-Lussac and the Avogadro's principle. So according to Gay-Lussac's measurement, they recognize that there was some diatomic molecules that it was thought to be like single atom molecules or just the atoms in the gas phase. And like this, it was possible to correct some of the mistakes done by John Dalton and improve the atomic weights known at the time in the 18th century and the beginning of the 19th century. But also we know that during the 18th century, several gases were already known and measured, and even Gay-Lussac himself was experimenting with them. And those gases were mainly nitrogen, hydrogen, oxygen, and chlorine. And some other metals were discovered, like for example, cobalt, platinum, nickel, manganese, and so on. Mainly these metals were discovered in Northern Europe. And then we should remember that in this region, for example, in Sweden, there was a very strong mineralogical approach for chemistry, and not only from the academical point of view, but also like in industry, mineralogical industry or geology. And we know, for example, that Berzelius, he was Swedish, and he was responsible, or he discovered some elements during the first decade of the 19th century, like for example, cerium and selenium and silicon. But also during this first decade of the 19th century, other elements were discovered like sodium, potassium, boron, palladium, rhodium, and so on. So it's in this way that by 1830, so almost middle of the 19th century, around 55 different elements were recognized and they were characterized. And during this characterization, they found that their properties, not only physical properties like atomic weight or density, were significantly different, but also chemically. Some of them were inert, some of them could react with alcohols, while others were not able to do so. And during the previous session, we saw that, for example, in the when we studied the history of organic chemistry, there was all this development of the theory of types that resulted from the study of the chemical properties of the elements and molecules. So by the 19th century, it was quite clear that the 55 elements, there were different groups of or types of molecules that they could resemble each other, while others were totally different. So it was needed to organize these elements, and the first to attempt it was John Dalton, but now with the new series of elements discovery, it was Johann Wolfgang Dobereiner, a German physicist and chemist, who did a first attempt to try to cluster groups of elements by their atomic and chemical properties. For him, it was clear that, for example, it was clear that some groups of elements, they share some chemical properties, like for example, bromine, chlorine, and iodine, they all react in a more or less similar way. And if you take a look at the atomic weights, there was also visible a clear trend. Like if you take the average of the atomic weight between iodine and chlorine, you will find that this value is quite close to the one of bromine. And based on this, he developed a theory or a concept called triads that we will talk in the next slide. Dubereiner went further and he could find other two groups of triads. Like this, he found that also calcium, strontium, barium, and sulfur, selenium, tellurium, they share this pattern of atomic weight, which increased uh, symmetrically, and that their chemical properties were also similar or follow a similar trend, like the case of chlorine, bromine, and iodine. He and other chemists, they went to search more of these triads, but they were unsuccessful. And therefore, for the chemist community, it was seen that the triads were just a mere coincidence and not a deep understanding of something happening with nature itself. For this conclusion, we must recognize that it was also propelled by the situation of the 19th century, where chemists were not able, or many chemists were not clear enough to differentiate between some chemical concepts. Like for many of them, it was confusing the terms of atomic weight, equivalent weight, and molecular weight. And if based on these problems, it was Kekule who recognized that if there was not an agreement between chemists about how to measure these basic properties of the elements, then, for example, his own theory of molecular structure, it couldn't take place, or it was more difficult to understand and to communicate chemistry. Therefore, Kekule, he promoted the development of the first International Chemical Congress, which was held in Germany. And the main goal was to reach an agreement on empirical formulas and to reach an agreement on the arrangement by increasing atomic weights of the elements. For this conference, uh, around 140 chemists attended, who were mainly the most influential chemists in Europe at the time. And, and after the conference, it was an agreement on these two aspects that could help to the communication of chemistry between Europe and the world interested in these fields. It was, for example, John Alexander Reina Newlands who did the first attempt to organize the elements by their atomic weights. More precisely, he did this arrangement for the first time in the 19th century because you remember Dalton's attempt in the 18th century. But more important, what he did is he arranged the elements by atomic weights, but in groups of 7 elements, and he called it the law of octaves. Uh, by doing so, he was able to produce the table to the right, where it was seen that some trends were visible, something similar to the triads, but not exactly the same. So when he arranged the elements in this fashion, in this manner, you could see that in some of the rows, horizontal rows, some elements of similar chemical properties were mm, set together, or there were some groups of elements that share chemical properties, like for example the case of sodium and potassium, but also for example fluor and chlorine, and sulfur, selenium. So some of the elements that they were known like to have some similar chemistry by the chemists of the 19th century, they could be seen in the similar uh, rows in this table by Newlands. However, because not only similar elements were in the table, but also very dissimilar ones, then for the chemist, again, it was seen that this was just a mere coincidence, and, and this approach was not taken deeply enough. However, it was found useful to reproduce or something similar happened to other attempts of organizing the elements. Like, for example, diagram presented by a French geologist called Alexander Emile, who organized the elements in a circular arrangement, and he found that elements of similar chemistry or with similar properties, they were aligned in the columns, in the vertical lines of this arrangement. However, he could see this in his arrangement. He was not able to publish it, so his work was unnoticed. Someone who was more successful at presenting his results was Julius Lothar Meyer, a German chemist, who developed the concept of atomic volumes. And what he did was to plot atomic volumes versus atomic weights. And by doing so, he was able to see this figure in the right of the slide, where you find some spikes formed by the alkali metals. And what is interesting in this figure is that despite at first there are some similar, or I mean the law of octaves, it was satisfied because between each peak there were 7 elements. Uh, there were other periods where the amount of elements was larger, and by this plot by atomic volumes, it was possible to conclude that the law of octaves, it was not necessarily the true, but periods of larger amount of elements was needed to represent the elements by atomic weights. Meyer was successful at presenting this publication, and it was recognized by the chemists at the time that there was necessarily some information that must be considered for understanding the chemical properties of elements and the periodicity. So from this plot of Meyer, you can see, or he concluded that, for example, hydrogen, it was the lightest element, and therefore it was the first in the left. And he by himself he could form like one single period by himself. But later, from lithium to sodium, you can find that if you count lithium, beryllium, boron, carbon, nitrogen, oxygen, and fluor, you have 7 elements there. And if you and this will build the second period between lithium to sodium. And if you analyze from sodium to potassium, you will find magnesium, aluminum, silicium, phosphorus, sulfur, and chlorine. And again, it forms 7 elements there. But from that on, you will find that the periodicity is not made by series of 7 elements, but more. Like, for example, between potassium, after potassium, you will find calcium, titanium, vanadium, and so on. And is this precisely the error made by Newlands? And despite this important contribution by Julius Lothar Meyer, there was a Russian chemist called Dmitry Ivanovich Mendeleev who made a very significant contribution to the development of the periodicity and the periodic table of the elements. We can say that the main contribution of Mendeleev for tackling the problem of organizing the elements was his decision to take or to give priority to the valence over atomic weights. So in the case of Meyer, we saw that there was a clear connection between periodicity and chemical properties of the elements. But before Mendeleev, every attempt to organize the elements was directed by the atomic weights of the elements, most likely as a conclusion of this Congress in Germany in the 1860s. But in the case of Mendeleev, he recognized also the importance of the atomic weights, but he gives priority to valence. And you can see that from some elements where he decides to switch between elements at the time of organizing the periodic table and based barely on the valence of the element. This was clear if you see at the periodic table or at the plot of Mayer that when you go between one period to another, there is a clear trend of valence. Like for example, if you check in the Mayer's table between lithium and sodium, you will find that lithium has a valence of 1 and then starts to increase. So beryllium is 2, boron is 3, carbon is 4, but then starts to decrease again to nitrogen 3, sulfur 2, fluorine 1, and then back to sodium 1, where starts the third period, according to Mayer's plot. So what you can see there is that clearly there is an influence of the valence, which also dictates the chemical properties. You should remember the way how valence was determined in the 18th century. And then this was the main variable for Mendeleev at the moment of organizing the elements in the periodic table. But more important, that he was the first to publish this way of organizing elements. What is more important in his work is that he left, for example, some gaps in his table, and he called them like there was some elements that were missing, that they were not discovered yet, and even he was able to predict some of its properties. He called these elements like eka boron, eka aluminum, and eka silicon, meaning like there was missing one element which was close to boron, or one similar to aluminum, and another similar to silicon. And then I think this was the key factor for the chemical community to accept his table, because later on, with the development of other techniques like spectroscopy, it was possible to detect some new elements that fit very well with the predictions made by Mendeleev. So in conclusion, we can say that his major contribution was on organizing the elements in the periodic table, but more important, on his decision to make this order based on the valence concept developed in the 18th century, and his predictions for the missing elements that were confirmed by further experimentation with techniques like spectroscopy. At the time, spectroscopy was a new technique. It was just under development, and we can say it started in 1814 with Joseph von Fraunhofer, who was testing the prism he was producing. And what he did is like he allowed to to light to pass through a slit and then through the prism. And with this, he could produce what we know today like a spectrum. Later on, it was used by chemists like, for example, Gustav Kirchhoff and Robert Bunsen to characterize different minerals. So you should know from the lab practice that the burners we use today in every lab in the world is called the Bunsen burner, and it's after his name. And Gustav Kirchhoff, you should remember him from previous session because he was one of the first to produce a catalytic reaction for the decomposition of organic compounds using acids and higher temperatures. With this new technique, then Kirchhoff and Bunsen could discover some new elements, like for example in 1860 they discovered cesium, meaning sky blue, because it was the most prominent line in the spectrum, and in the 1861 they found rubidium, meaning red, for the same reason, like red was the most prominent line in the spectrum of rubidium. More important, in 1875 the German Paul Emil Lecoq, he discovers gallium. And what is important about this discovery is that this element, gallium, it matched perfectly the predictions of Mendeleev. So it could be placed in Mendeleev's periodic table neatly, and it supported the concepts and the ideas developed by Mendeleev. Other two new elements supported and completed Mendeleev's prediction, and it was germanium and scandium. Until today, spectroscopy is one of the basic and most important techniques for the characterization of materials, not only for the identification of atoms, but also for the identification of molecules, and its use in different techniques, like for example in infrared spectroscopy or in Raman or in different techniques like photoluminescence and so on. And with these techniques, what I want to say is that it's not only about the light which is emitted by the compounds, by the, let's say, a molecule, but it's also the light which can be absorbed by the molecule, which can be used like a fingerprinting for the identification of molecules. Like for example, in the case of Raman spectroscopy and infrared spectroscopy, the basic principle is that in the case of the infrared spectroscopy, what you do is an absorption of light or energy in precise wavelengths, which gives a spectra which can be measured by the detector. But in the case of Raman spectroscopy, what you have is a scattered light from the sample, which is shifting the light of the source. So let's say you have a laser which is shining a surface of a material, and this laser is 532 nanometers in wavelength. But the light which is reflected or scattered from the material, it is different wavelengths, and these different wavelengths or colors are the fingerprinting of the compound which is under investigation. Still, Mendeleev's periodic table still had to withstand the inclusion of two new groups of elements. One of them is the rare earth elements, that we can say that their discovery started in 1794, so much earlier than the table proposed by Mendeleev, when Johann Gadolin discovered a new metallic oxide in a quarry near East Stockholm called Ytterby or something like that. And this oxide was known at the time, but the element yttrium was only produced or isolated 50 years later. So it placed the discovery of the element near in time with the development of the periodic table of Mendeleev. Similarly, between 1830 and 1850, it was Carl Gustav Mosander who discovered what he thought to be four new rare oxide or rare elements. They were lanthanum, erbium, and terbium. And he believed there was a fourth one, which was didymium, but later it was Carl Hoyer, who discovered that this was not a single element, but in fact it was two. It was composed by praseodymium and neodymium. Later it was Lecoq who discovered samarium and dysprosium, and Per Theodor Klett who discovered holmium and thulium. So at the end of all the discovery of the rare earth elements, it was found that all of them they share a common property of having a valence 3. So it means that they should be placed in one single column. However, their atomic weights was very close to each other. So it means that they should be placed in a single horizontal row in order to fulfill the requirements of Mendeleev's periodic table. So the easiest solution was to create all a new group for the rare elements like we see today in the periodic table. The second group of elements that was discovered after the invention or the invention of the periodic table by Mendeleev, it was noble gases. The first noble gas to be discovered was argon by the cooperative work between Lord Rayleigh, we know him better like Rayleigh, and William Ramsay. They were working with nitrogen, and Ramsay tried to reproduce some experiments developed by Cavendish. Maybe you remember him from a previous session that he was working with the hydrogen which evolved after the reaction of metals with acids. And so Ramsay tried to reproduce some experiments of Cavendish with nitrogen, and he discovers that one bubble of air or gas which was produced during some chemical reactions, it was inert, and it was not possible to combine this gas like he did with nitrogen, for example. So he was working with nitrogen and trying to combine nitrogen with different gases, like for example with oxygen. But he saw that in some of his reactions there was a gas which he couldn't mix with anything, so it was inert gas. And that's why Ramsay, when he reproduced these experiments, he took this gas and heated up, and with the use of spectroscopy he discovered that in fact it was a new element, and he could determine the atomic weight like 40 and the valence 0, as it could not react with anything else. And if the valence is 0, then it will fit better between the halogens and alkali metals. So you have the trend between sulfur, chlorine, and now the new element which will be argon. And then on the next period you will find potassium and calcium. So you will have this trend of valence between 2, 1, 0, 1, 2, which is seen today in the periodic table. Later on, William Ramsay, in 1895, he discovers Greek, which is a Greek word for sun. And this is a name which was given by an astronomer called Joseph Norman Lockyer. And it was the name, even though the element is assigned to helium, he was the first to produce this or to recognize this gas. The name was given by the astronomer because This astronomer took the spectra from the light during a solar eclipse, and he could deduce that the atmosphere of the sun there was helium. So when Ramsay could identify this compound on Earth, it was the first time that it was seen in Earth, yes. And at the same time, it could be seen like a final conclusion, or yeah, to go against this idea of Aristotle that the heavenly bodies, they were perfect in nature and therefore somehow different than the reality we see in Earth. So this was a discovery that this sun, which is a heavenly body, uh, is made of the similar elements that you can find on Earth. Later on, Ramsay also discovers, or yeah, discovers neon, krypton, and xenon. And neon is the word for new, krypton for hidden, and xenon for stranger. Mm, these discoveries of noble gases also had like a practical application. Like it was George Cloud who applied electric currents to tubes filled with noble gases, and he was able to produce color lights. And these lights are like a symbol of the 19th century, where now cities are mm, colorful with the application of these noble gases in tubes. From the 18th and 19th century, we recognize that the fields or the science of physics and chemistry, they were separated fields, separated works. There was not a so clear connection. And even by definition, it was stated that physics is the study of those phenomena that didn't involve the change of matter, while on the other hand, the field of chemistry, it was the study of those phenomena that change matter through chemical reactions. However, if you see closely, this line or the division between both sciences is sometimes not so clear, not so evident. And there are some examples in the 18th and 19th century when, for example, the study of electrochemistry necessarily involved both phenomena, and that today we can see that the two fields are closely related. So in the 18th and 19th century, chemistry was devoted to the discovery of new elements, like we just discussed today and the session before, and also in the development of techniques to break down complex organic compounds and how to represent these molecules, like for example with the structural formula by Kekulé, but also in the synthesis of those molecules, like we saw with Berthelot and fats and oils during the previous session. But in the field of physics, the main topic, or at least the topic which was closer to chemistry, was the study of the flow of heat. And this study was defined like thermodynamics. In the field of thermodynamics, we recognize three main contributors. They are James Prescott Joule, that we still use his name Joule for energy, Julius Robert von Mayer, and Hermann von Helmholtz. From their work, it was derived what is known like the first law of thermodynamics. We know like the law of conservation of energy, according to which energy cannot be created or destroyed. Second, after this first law, we must highlight the contribution of Rudolf Julius Emanuel Clausius, who developed the concept of entropy, which he defines like the ratio of the heat content of an isolated system to its absolute temperature. And this definition is important because for him, he could see and experience that there was a spontaneous flow of heat from one point at high temperature to another point at lower temperature. And I just say that this thermodynamics, which is a topic of physics at the beginning, is closer to chemistry, because even though the sun is the main source of heat in the solar system, it's also true that during the chemical reactions there was a clear evidence and perception that there was a source of heat, and the heat could be consumed or produced during a chemical reaction. So with the work of Rudolf Clausius and this spontaneous flow of heat, we built what is known like the second law of thermodynamics, in which in any spontaneous energy change, the entropy of the system will increase to a thermodynamic equilibrium. And as you know, then this is like a solid background to the study of chemical reaction. The first to develop the connection between the laws of thermodynamics and chemistry, it was a Swiss Russian chemist called Henry Hess. He did quantitative measurements of reactions that evolve heat during the chemical process. And by this, he came to the conclusion that the quantity of heat produced or absorbed in going from one substance to another was the same no matter by what chemical route the change occurred or in how many stages. And because of his work, he is considered like the founder of thermochemistry. Another important conclusion from the second law of thermodynamics is related to the spontaneous direction of reactions. According to the second law, some reactions occur spontaneously in the direction of entropy increase. And for Berthelot, who was a significant chemist that we discussed in the previous session related to the organic synthesis, the synthesis of organic compounds, uh, in the 19th century, he turned to thermodynamics and his measurements using the calorimeter, which he developed himself, was that the spontaneous direction was related to the heat production. So those reactions that are spontaneous necessarily involve the production of heat. So they were exothermic, as we call them today. However, uh, even though it is true in many cases, it's not always like that. So we know today that there are several examples where the reaction can be spontaneous and endothermic, so it absorbs heat. And this type of reactions, to understand this phenomena, you have to know that this is true when the change in entropy is much larger than the change in enthalpy. So you should recall the equation uh, of the free Gibbs energy, but you can find it here in the slide in the bottom. Finally, another aspect which was not considered by Berthelot about when he was working with the spontaneous direction of a chemical reaction is related to the existence of reversible reactions. And the first to highlight this importance was Alexander William Williamson, who working with, let's say, two reagents, let's call it A and B, he found that when he mixed these components, he will be able to produce C plus D in a spontaneous way. But if he started with the chemicals C plus D, then he will end up with A and B also in a spontaneous manner. So in this type of reactions, it was not obvious which is the spontaneous way where the entropy increases. And this situation is called like a dynamic equilibrium. And this is the basis for the development of chemical kinetics and the study of rates for chemical reactions. In order to quantify or to develop a model to understand this process, two Norwegian chemists called Maximilian Guldberg and Peter Wage developed what is known like the law of mass action, and they define what we use today like the equilibrium constant. So what they did is that they tried to explain this process using the amount of reagents present in the solution, and not only like the mass, like it was tried before by, for example, Berthollet, but by concentration. So they created this equilibrium constant as a ratio of the product of the reagents and products in a chemical reaction, as we see in the slide and as you know from your lectures in general chemistry. This equation was useful to establish a relationship between the rates of chemical reactions, like if, for example, if a reaction is going to the right, so A plus B is producing C plus D, and this rate of this reaction is much larger than the opposite reaction, the C plus D to produce A plus B, then at the end of the reaction you will have more higher concentration of the product C plus D, and the equilibrium constant will have a larger value. And if the rate is higher in the other direction, then you will end up with higher concentrations of A and B, and the rate constant, or the equilibrium constant, sorry, will be opposite to the first case. Next step was given by Willard Gibbs, who was an American physicist who developed the concept of free energy and chemical potential. And free energy is defined like the free energy or the energy available to do work, while the chemical potential is the rate at which free energy changes as the concentration of a particular substance changes. With these concepts, then he developed a framework on which the chemical reactions move spontaneously from a point of high chemical potential to one of lower chemical potential. This is important because it can consider the heat flow that was found to be important for the reactions measured by Berthelot, but also involves the effect of concentration in chemical reactions as deduced and as we discussed for reversible reactions. So in this way we can uh, enclose or we can analyze exothermic reactions that are spontaneous but also endothermic ones. Another important consequence of the work by Gibbs is that free energy is much easier to measure than entropy. Therefore, for example, the physicist Walter Hermann Nernst, he found a way to calculate the free energy from the current produced by a chemical reaction, which is not the case for entropy. Despite the importance of the work by Gibbs, it was not immediately received by the European chemists and physicists, and it took the time for the translation, mainly from Henry Louis, who took Gibbs' work and translated it to French in 1899. And not only translated, but also complemented and developed what is known like Le Chatelier's principle, according to which if you have a system in equilibrium and you introduce a perturbation to that system, like for example, changing the concentration of the one component or changing the temperature or changing the pressure, then the system will rearrange itself in order to minimize the perturbation and reach an equilibrium. And finally, another topic which was developed during the 19th century is that of ionic dissociation. And on this topic, first we should talk about the contributions by François-Marie Raoult. We know him by the what we call like Raoult's law, and his work he was focused on the study of the freezing point of solutions. And what he saw is that the freezing point was depressed in proportion to the number of particles or atoms, molecules, ions of the solute present in the solution. And even more, he saw like if he compared the depression of freezing point of a solvent with sodium chloride or with sugar, he saw that the depression caused by the sodium chloride, it was double than that of sugar. So it was also like a non-direct evidence of the presence of atoms in a solution. And this is important because even though all these chemists during the 18th and 19th century had developed all these theories that finally we know most of them are correct, but during their times, there was not an evidence of the existence of atoms measured directly. So the atomic microscope, it was developed much farther or farther, not at this time yet. So they developed all these theories without actually seeing the atoms. But it was through this type of works, like for example, Raoult, that it was possible to conclude that in fact there is some atoms which are dissolved, for example, in a solution. Another physical phenomena that could support the presence of these atoms and even could measure the mass of some of the molecules it was done by Albert Einstein when he tried to, or when not tried, no, when he could explain the Brownian motion of particles in a suspension, in a solution, in a suspension. So what he was able to show was that this Brownian motion in a suspension was caused by the bombardment of, for example, water molecules to the walls of the particles, and that's why there are some erratic movements of the particles in the suspension. And this was important because even at this time, there were some important chemists and scientists who made great contributions to chemistry, like, for example, Friedrich Oswald, who at the beginning, he didn't believe in the existence of atoms. So he was sure of the relevance of atoms in the sense of instruments for the calculations of chemistry, but there was not a clear evidence for him until this time for the existence of atoms. Uh, and then this type of measurements like Raoult or Einstein, then it could demonstrate that these particles, let's say it like this, when you say the particles in this sense, in this context, you have to refer to atoms or molecules or ions. So these particles, in fact, they exist, and some of their properties could be measured. Like, for example, it was measured the atomic weight that we discussed at the beginning of this video, but also in here there were some contributions to measure, for example, how how fast the ions can move through a solution, or, for example, with Einstein, the bombardment of these molecules to a particle in suspension. So Raoult, he gives this law, Raoult's law, according to which the partial pressure of a solvent vapor in equilibrium with that solution is directly proportional to the mole fraction of the solvent. Another important contribution on this period, it was done by Svante Augustus Arrhenius. We call him just Arrhenius. And since Faraday, it seemed that electricity existed in the form of particles. So if you remember in a previous session when we discussed about Faraday and his contribution to electrochemistry, he gave the name of ions to these so-called atoms of electricity. But the precise nature of these ions was not certain, and it was Arrhenius who proposed that these ions are no more than the groups of atoms or atoms themselves with an electric charge. And he did so even before he finished his PhD, and when he tried to publish it, it had a lot of opposition, like from the referees and from academics. But it was Frederick Oswald who recognized the importance of Arrhenius' work, and he invited him to continue in this direction. Another important contribution of Arrhenius is the concept of activation energy that we use today. So what he says is that the fact that there are collisions between particles, meaning atoms, molecules, or ions, is not enough to guarantee that there will be a chemical reaction. And he says that there is necessarily an energy barrier, which is called an activation energy, which is required for the reaction to proceed. And this was found again very useful for Oswald, who was working with the field of catalysis, and he concluded based on these assumptions that during catalysis, the formation of the catalyst combined intermediate requires a smaller energy of activation. So what you see now at the end of this session is that most of these chemical concepts and these laws like Raoult's law and all these findings that we discussed in this session are the very basic background on which we still work today. So at the beginning of the semester, we started with a period of thousands of years ago, but we are now approaching the science that we are doing still today. And this has been a long journey, but still in the next sessions, we will talk about other phenomena and processes that were discovered recently and that we use today in our labs every day. So thank you so much for your attention and see you next time.